So there are 9 regions, and this is x-axis, this is x0, x1, x2, and x3. And this is a first interval, and second interval, and third interval of x-axis. Same thing. Here's the y1, y value, y2, y3, which is 4 there, very small. So each of this region, the construction cost is different. It is given by this formula. So if you are here, let's say if I'm here, that's for the x, that's the second 1, 2, 3, that's the third interval, right? That's right. And for that one, this is a second interval, so calling is a 2, 3, third region. So this will be 2, 2 region, right? 1 and 2, second interval, 1 and 2, and second interval. That's how it was labeled for Riemann sum the other day. So, for example, if you're here in 2, 2, 2, 2 region, then you're going to plug in I equals 2 and j equals 2 to get the cost. Okay? So what is it? Negative 4. That is 2, so that's 8. That's negative 8, right? This part. And that's 16 minus 2, so they cancel. So that's 6. Is that positive 10? So for example, in this region, the construction cost is a $10,000 per square feet. But what is the area of this one? If you assume this is a square feet, that's probably what you have assumed. So that's 2 units and 1 unit, right? So it has area 2 in there, correct? So if you multiply 10 times 2, that'll be $20,000 gonna cost to do the construction for that middle region. So if you go here, that's second and third, that's 2, 3 region, right? So you plug 2 and 3 in there and multiply by this area. What is the area here this time? 2 by 2, right? So area here is 4. And if you multiply 4 by this rate, then you're going to get actual costs for that region. So we do that boring calculation for each of these 9 regions, add them all up, then that's how you get the number. Were you all able to access my solution file? Yeah, so that's, what was the answer? Yeah, so that's the total, turns out, if you add them all up. This one is area 1, right? These are all area 1 here. This is area 2. This is area 4. 2 and 1 and 1 and 2, things like that. So you multiply that area to the construction cost and things like that. So makes more sense after I explain like this. Of course, it's more challenging by reading unfamiliar context. Yeah.
Where exactly is the negative 4 and the 8? Where'd you get all that?
So if you're in this region, so I here is 2. Every this region, this I is 2. From there, the j is 2 here. So I is 2, j is 2. You plug it into this formula, you get the rate. So if you plug in I equals 2 and j equals 2 there, and you got this number 10. So this $10,000 per square feet if you're doing construction right in the middle here. But the area here is a 2 square feet. So you've got to multiply 2 there, and that's a $20,000 it's going to cost to the middle part. Yes? All right, so it's not quite in the standard form of the Riemann sum, because Riemann sum usually involves this one in terms of xij, right? But we can still write the sum in summation notation. I think is a good thing to do. The total cost is the sum of I going from where to where? 1, 2, 3, right? Correct? And j is independently running from 1 to 3 as well, right? And we're multiplying area here, right? So let's first, the rate, rate is negative I squared plus 4i minus 2j squared plus 8j minus 2. That's the cost per square feet. Now you have to multiply the area of this region, right? How do you write the area for each of the, if you're in, for example, ith interval for x, there will be xi minus 1. That's delta xi notation, right? And for if you're in some way, this length would be delta yj for jth interval you chose. So that would be sigma notation for the total cost. And this is how I calculate it. Just type this thing into calculator, computer Mathematica, and then get the answer out of it. But if you do it one at a time, you feel everything about what's going on here. That's much better than what I did. Make sense? All right. So why on earth did I assign this thing, you think? This problem. Yeah, double integral. For example, if you have this big regions, and here, if you choose just random x comma y, suppose f of xy represent the cost per square feet. But this size here is even less than, maybe it's a centimeter wide, very, very small. But still, it makes sense that it's going to cost $200 per square feet. That still makes sense. If this area is very small, you'll be multiplying very small quantity to that rate, $200 per square feet, if it is very small, right? So whatever the area we're looking at is a lot smaller than feet, is like 100th of a feet. And here you multiply that area to the rate, cost it in there, and then you keep adding it in there. That's exactly the definition of forming a Riemann sum. So if you have a cost function per square feet, if you choose some random points in there, this function tells you, because of the surface condition, what's underneath the ground, it's going to cost more in here. Suppose you have a function, the meaning of this entire region D, and we have cost function per square feet, and the symbol dx dy, and this is going to represent what? There's a total cost. Total cost is going to do all the construction, right? But this is baby step toward to that idea, the Riemann sum. So maybe you get familiar with this geometry problem, so you don't have to think about the Riemann sum. But later, if you analyze and more problem that is not just a simple volume problem, and you will see the Riemann sum, it actually helps you. You analyze, slice this problem into little pieces. You analyze it, the formulation, you got it here. Oh, that's exactly Riemann sum. So whether it's a volume or whatever, because it looks like a Riemann sum, I can pass to the double integral, and to calculate that double integral, you will use iterated integral, stuff like that. So to some people, this analysis is very natural, not necessary to pass the Riemann sum, but from my experience, thinking about Riemann sum is not a bad idea. It's going to actually help you to analyze a problem that is not just straightforward volume problem, like a density problem or work problem, like in the physics problem. Any question about this example and the purpose of this example? Make sense? Riemann sum? Yeah. So this is another example. In a sense, what it takes is a one variable integral calculus, but it is in the context of a two variable, right? Okay, so we start with a two variable function. We stick in x equals pi, then it becomes one variable function, just like when you're doing partial derivative, right? You stick in x equals something, and you differentiate this one with respect to y. That is called partial derivative with respect to y. Now we're doing partial integration or something, but they never call it like that. But I think we can call it partial integration and putting it like that. Okay, so what happens here? 0 to 3, pi replaces x as y to the 5th, e to the pi in there, y to the 3rd, dy. You just have to integrate this one, right? I love pi because it's not simplified any further. It stays like pi forever, right? So it's the same as x, but X confuses student, pi usually don't. Pi substitution don't. But you recognize this is a number, right? And if it's a 1 or 2, disappears, it changes the shape, but pi is there all the time. That's why I like this one. Okay? So how did you figure this one out? What did you do first? Y squared times y cubed? Yeah, why did she separate it like the y squared time? Probably this y squared is something good, right? What is it? Right, u substitution. U here is y cubed, right? And its derivative is going to match the y squared. It's going to knock that down. So it simplifies a little bit. And what is left here is exactly how substitution, right? What if it is not 3, but it was y to the 6th power? We're still in good shape because y to the 6th power is u squared, right? So that's still in, partial fraction, not partial fraction. Integration by parts is applicable. But this is simply u in there, right? So this is how I do. First, you differentiate du and dy like that. And that's 3y squared, right? And next stage, when you enter integration with respect to u, this has to change in terms of u. So I emphasize it like this. This is a standard notation. What is u when y was 0? So that's 0 there, right? If you plug in there, correct? When y was 3, what is u here? 27. So I like this notation because at this point, emphasizing that we're switching to u and letting you know that what this variable is standing for. Fair enough? Now, once you change this limit, this thing must change to du. It's a very important use of notation that, reflects how you're understanding this process. Then you keep all this thing there and multiply the reciprocal of this one. That's how it works. Reciprocal of this one goes like this. So I skip all this du dy manipulation because you always end up in multiplying the reciprocal things. So skip all that. Since we understand what it is, just go directly to this one. It's very quick. Here's your thing, multiplies reciprocal. And this reciprocal is called, it has a fancy name, Jacobian factor. That's right, this is a Jacobian factor. All right? So because of this cancel, leaving y to the third, that was whole motivation, right? Okay, so now switching to just this number, and if you cancel these two, we have 3 out there and y cubed and e to the pi y cubed, and we emphasize it here. That's right, 1/3. All right. Fixed it. All right, I'll pull it out eventually. So remember, when you're integrating this one and then you're in u, this must be written in u, right? Before you integrate it. So you have to pull out the 1/3 there, 127. Then this is in u like that. And that is in pi times u like that, and du. Once you write everything in terms of u, then you can integrate it with respect to u. But you have to make sure that, I don't like this y part, I'm going to pull it out. Nothing like that. You have to write everything in terms of u. If it is really a absolute constant like this, you can factor that out. All right? From here is integration by parts. So it's 1/3. I will integrate this part first, so when I differentiate that one, it becomes simpler. I wouldn't integrate that part first, right? It makes it even more complicated. Fair enough? Yeah. So if I integrate that part, what is the function? 1/pi e to the pi u. Make sense? That's what it is. Yeah. If you differentiate this one, you can see pi cancel, you get that one back. So I only integrated this part alone, and you have to evaluate this one at 0 to 27. And no need to go back to u or anything. You substitute it, your indefinite integral, just play with the number that is replaced. It's minus, right? And 1/pi 0 to 27, That one is now differentiated, become 1, and is leaving this part, and I claim that part is now easy to integrate. And I will leave this, that evaluating all that. It's easier from here. All right, so it's easy. What is the antiderivative of this one? 1 over pi squared, maybe, right? E to the pi u, fair enough. And evaluate the 0 to 27. So if you combine all that, you get this answer. And that's why there's 27, right? That's the answer. Fair enough? Okay. Any question? Yes. 1 over pi here? Or this part? Yeah. Think about, if you differentiate e to the pi u, you get pi times e to the pi u, right? So you don't have just e to the pi u. But when you're integrating this part, and that means derivative of this part is supposed to be e to the pi u, right? Nothing else. So think about how you integrate a sine 2u. What is the integral of sine 2u? Negative cosine 2u, right? That's the integral? No? You have to multiply by 1/2. The same thing. Make sense? Yeah. Anything else? This is substitution, integration by parts. What is the other one that everybody hates? The integration technique. Right, partial fraction decomposition. And right in between those two things, there's a trigonometric substitution, right? Yeah, trigonometric substitution. Well, when you're going to do polar and cylindrical coordinate, they're coming back, and yeah, they'll all come back. But now partial fraction decomposition, as far as I know. All right, those were 2 homework problems. Any question about homework problems further? Yes. No, that's not what I do. Yeah, because hyperbolic functions used in engineering of other purposes, but it's all the same as just exponential and complex, and they do combine it all together later. So I'll just leave it at that. So I don't go into hyperbolic. Too many formulas and plus minus is too confusing, if you know what I mean. All right. So I just wanted to explain the meaning of that integral we just did. I asked you to, you did it, but here's the meaning of that thing. This is the 2-variable function. Y cubed times e to the x. No, the other way around. Y to the 5th, e to the x times y to the 3rd. Is that right? That function, the graph looks like this. All right? What we just did, this is equals 0. What we just did is I put a plane, the perpendicular plane. Do you know what perpendicular plane I inserted here to get a cut? X equals pi. Thank you. So here is the graph. Z equals y cubed, 5th e to the x y the 3rd. Here it is, right? But we evaluated x equals pi there, right? So there's a surface, but I'm going to pretend x equals pi is here. This is where x equals pi. And y is varying. As you go from here, x never changes. X is pi all the time. But y is changing. It's this kind of different orientation. So if you erect plane, I call this plane H-plane. Remember that? H-plane. If you erect that, I hope you see that is kind of cut out this surface there, giving you a section, right? The section is a curve. Okay? So that curve is sketched here. This plane is H-plane, right? That's how I named this H-plane. But it has a good equation. What is the equation of this H-plane? Anybody know the Cartesian equation of this H-plane? No, the equation of the H-plane. That's the equation of this guy. Right, perpendicular. But there's a Cartesian equation. Something equals, just like 3x minus 4y equals 0. Remember that part? Yeah, this is a plane. What is the Cartesian equation of this plane? This is actually sketched in, yeah. It's sketched here, right? So what is the equation of this plane right here? It's very simple. Y equals pi, almost. X equals pi, right? Remember we call x equals pi, and then this plane is where everything x equals pi. There is no x minus or y component to the normal vector, nothing. So what is the normal vector of this plane? 1 comma 0 comma 0. That's the normal vector of this plane. The question, Andrew? Makes sense? So does that make sense? Where every point on this orange plane is z equals 0, right? Here x could be pi, but somewhere else you can easily imagine x not going to be pi anymore. So this is not correct equation for the orange plane, right? So let me sketch xyz plane in here. Here's x. Thanks for the question. Where's x equals pi? This is x equals pi, right? Where's all the other lines? Let me change it so that it looks like that. X is over here, y is over there. That's probably not correct orientation, is it? The thumb rule, whatever. But let me correct this. I don't want to put the incorrect thing there. X equals pi there. This is where x equals pi, and think about all the points at x equals pi. You got to remain in this line, right? That's where x equals pi. But y is changing, as you can see, right? Y is changing, correct? So every point in here, x remains pi, but y is changing. So this is still valid. X is pi, right? All the points. How about points directly over these points, right? Still x equals pi, even though z is changing. So the plane you can imagine, which is containing this bottom line I just described, and perpendicular to the orange plane, is x equals pi, the plane. So if you change it to usual our plane equation, these are the coefficient 1, 0, 0. That's a normal vector. Yes, Tony. So we use that to trace it, x trace and z trace and y trace, to kind of dissect these surfaces to understand in terms of curves. So this makes sense? So if you make that cut, so this is now graph z equals f pi y, right? You plug in x equals pi in there. Now this axis is a y-axis, and that axis is a z-axis. We're looking at this one variable function. Z is now one variable function as you specialize x at pi. Make sense? Okay. So what's the meaning of that thing we just calculated there? 0 to 3 to fx f pi y dy. Area underneath y equals 0 here. Y equals 3 over there, as you can see, is exponentially grows way higher, but eventually it's bounded, right? All the way up there, somewhere in the galaxy, it's gonna meet, and there's area underneath it, correct? Yeah, so that's the area under the curve. The curve is the section with this plane parallel to some coordinate planes. Fair enough? That's what that's measuring. If you specialize it and put the one variable integral. Okay, let's keep going. Seems like it makes sense. I think it's in wrong order. Alright, so I want you to do this part yourself. Exercise, just the one exercise, because individually is fairly simple. This exercise number 1. New notation is just introduced. This d equals this interval cross interval. This product is called Cartesian product. And they use this notation. So let me explain here. This is y-axis and this is x-axis, right? The first one, is the x-axis. 0 to 2, that's the interval there, right? And the second one is for y-axis, 0 to 3. Fair enough? So you draw this line, x equals 0 and x equals 2, vertical line. For y, you draw a horizontal line, x equals 0 and x equals 3. And they form rectangular region. So they use this notation conveniently to represent rectangular region. 0 to 2 times 0 to 3. What is the name of this product? Cartesian product. Okay? So they describe rectangular region using this Cartesian product notation. And here's a function, right? So what kind of function is that? Two variable function? The better name? In terms of degree, this is a linear. Excellent, that's what I was looking for, linear function. If it's a linear function, how does the graph look like? The graph is planar. It's a plane. It's a plane there, right? All right. So do you see four corners I'm talking about here? Where's the four corners? Here's one corner, here's another corner, another corner, right? So I'm asking you to plot the points over this four corner. This is xy. Z coordinate is coming toward you, right? Z coordinate. And evaluate what is z here, what is z there, what is z there, what is z there. Then go to three-dimensional space and see what kind of thing is above this rectangular region. Does the first part make sense? Does everybody understand how to get the z? Yeah, you have xy coordinate there, so plug it in there. And finally sketch it. That's the point. Alright, was that okay? At over 0, 0, I got z value 5. Agree? If you plug in x equals 0 and y equals 0, you get 5 out of it. So over that point, the z coordinate is 5. So I looked at the 2, 0, I got z equals 3. And the other one over there in the upper left corner, z equals 2. All the way up there in the first quadrant, z value is 0. Agree with those values? So I went to three-dimensional space and try to be relatively correct, not perfectly accurate. And I think I don't think it has to be a parallelogram. I don't believe. In general, it's probably not parallelogram, so you don't have to make it look like a parallelogram. Maybe it is. I think it is. There is this thing, diamond, hovering above this rectangular region, right? So that's the answer to this thing. I think it's a good technique if you are looking at function and they're given a region like this. How are you going to sketch it? You first look at the extreme point, use that, and use a little bit of imagination. Oh, if it is a quadratic, I'm just going to make it a little curvy. You know, if it is a linear function, you make it straight, and this is a fairly accurate picture. Any question about part 1? Fair enough? For part 2, I don't want you to actually calculate this one. I want you to, what we actually did it here. This automatically answered because of that. I'm talking about number 3 in there, just giving you the meaning of this one. This is where y equals e, right? Y equals e, and I'm going to use a different color. E is a 2.7, is that right? So this is where y equals 3. Y equals e would be slightly less than 3 there, correct? This is where y equals 3. The y's end up at 3 there, correct? So line, think about the line that y is all 3 would be the line is parallel to x-axis, right? So here's a 3 there going underneath it like this. Does that look like a line in that region D where y is all 3, only x is changing, correct? Now think about the plane that contains this red segment erected over xy plane is a perpendicular, right? So I go over from that extreme point, go perpendicular like that, meeting that. I go over there, perpendicular like that. So the section of this plane H is going to be straight line because of this is a linear function, right? Okay? So why did I do this? Because this thing measures area under, what is the name of this shape? Trapezoid? Yeah, this is a trapezoid shape. Area of that one is represented by this integral there. Yes?
So does it measure the area under that curve in the xy plane, or under that curve in the function?
No, if you turn this one around and the area of this this plate, that's what it represents. So under the curve, which is z equals f of xe, right? So it's a line. Yeah. Make sense? Yeah. So let's calculate that. Go ahead and calculate this one. Is the second part of your exercise number 1. All right. Was that okay? Yes. Yes. It's missing. Why is that? I just deleted it because of that, and then I didn't put it in there. It's amazing, but it is correct. Any question up to this point? Are you familiar with this notation, bracket 0, 2? This is very good notation because it's a linear notation, right? If it is a plus and minus, it passes, and the scalar multiple can go all out, so you can do business like this. This bracket is a linear notation. Linearity holds there, so you can pull out like that. X squared 0 to 2, and 3 plus 3 minus e. That's constant multiple, right? It goes past through that. This is a lot easier to calculate. It's a 2 times 2 minus 0, right? 1/2 minus 4 minus 0, right? Plus 3 minus e, 2 minus 0. So this bracket notation can pass distributed over scalar multiple and addition, and in my opinion makes this calculation a lot slightly simpler than plugging all e 2 in there and subtract the entire thing from the evaluation at 0. This is some neat trick to know to get to that. All right. So here is the shape, and we are dissecting into pieces and thinking about the area. That's what we've been doing. All right. So why are we calculating areas? I thought we were calculating volumes, right? But this is how it began. So I hope this picture makes sense. The graph of z equals f of xy, that's the top part. And this side is created because you have rectangular region down there, given by, for example, AB cross CD. This notation makes sense? This is rectangular region down there. Because of that, you have sliced, only this portion of this thing. That's a graph. Our goal is computing the volume of this one, right? What we have did so far is considering this plane H. Okay? So if we have to write down this equation, right-hand side, for example, I'm going to make up just constant number. What is the left-hand side? Is that x equals c for this one or y equals c? Is this x equals c? Are you sure? Is it x equals c or y equals c? It's x equals c, right? So x equals c is correct. Because if you look at this bottom line is parallel to y. Y is changing, x is not changing, right? So this is this x equals c. That's a Cartesian equation of this h. If I slice this one, then you're going to plug in x equals c there, right? So this c is incorrect. That's something different. Let's see, alpha. Alpha. So this area underneath this one would be c to d. This time, is that y is going from c to d or x is going from c to d? It's y, right? And f of, we're plugging in like x alpha, like a pi, and integrating with respect to dy. So this shaded area and the connection makes sense? Yeah, those are the homework problem and the exercise we just did. Correct? So that's the area. That's what they did. The summary, the general description of what we just did. Correct? So how do you go from here to the volume? Volume is defined as Riemann sum, right? But they're doing a slightly different approach. Why don't we take that one and increase a slightly thickness here, okay? Turn it into volume. Okay, they call this one AX, this value in here, like A alpha. So if you cut at x equals a, it creates this section. The area of the section at x equals a is denoted as like this, a of x or a of alpha. This is where x equals alpha there. Make sense? If you make that cut, we have this side. The area is this ax. You can calculate this one, keeping this alpha in general. And that's our function. Now, if you introduce slight thickness, what is a good notation for the thickness here? Delta x is incorrect, but delta is correct. Delta y, because this side here is parallel to. No, I was wrong. Delta x is correct, and I'm sorry. This is supposed to be delta x, because if you do that, that's it along with x-axis, right? So delta x is correct. Yeah, that was fun. There's a delta x. If you divide it, subdivide maybe irregularly, that's delta xk maybe is a good notation. So why did I do this? Why did I introduce slight thickness? Volume, right? The volume. What is the volume of this piece? Yeah, the area times the delta xk, that's the volume, thickness. This is called generalized cylinderized. So base times height. Height is very, very small in here. That is the area. Fair enough? Now what do? That's the only one slice, right? So you add them all up, correct? So you pass the total volume. Seems like pretty close to some of these slices, right? Yeah. So I'm going from I'm using k going from 1 through however many slices you made in there, and here's x and multiply by thickness delta xk, correct? And here, what are you going to use? Some sample in here. If you can use xk or xk star, doesn't matter. Whatever slice you choose in between the interval xk minus 1 and xk. Here it seems like I'm using xk, so you can replace it with an xk in there. But it doesn't matter, it turns out, because it's a continuous function. They all converge to the same number. So you may leave it like that for simplicity. Okay, so we analyzed that the volume was defined differently. Riemann Sum, dissecting all the bottom, reinterpreted, maybe this is also is going to work, right, like that. So if you just look at this one, is this a two-variable Riemann sum or one-variable Riemann sum? There's only one delta, right? So one-variable Riemann sum. This is one-variable Riemann sum, right? So that approaches, this one becomes stretch symbol, right? X is going from A to B. This is about X here. This one changes to dx, and this one changes to ax. Whatever is inside in terms of xk becomes a function, integrand function inside the integral. Whenever you see this shape, you can just pass to this the definite integral, right? So that's what I mean by Riemann sum analysis, right? If this is natural, you don't have to do that. If it is not natural, Riemann sum actually helps you to understand the various different formulation, which is based on just obeying how you go from here to there and giving up some, better understanding of why is it connected like this. It's just simply when you arrive at here, you can simply pass to this one. But it's not equal, right? It converges to that. This idea makes sense? So that doesn't look too bad. This AX here is a sectional area. Is that right? That's how I want you to remember. You've learned this in Calc 2. Section across this axis of rotation. That's exactly the same principle now. So I want you to keep this structure in mind. Integral of sectional area becomes volume. That's the idea, but also I want you to remember the volume is now written complicated. Here's AB. I want you to put the big parenthesis in there and dx out there. Makes sense? It looks just like this one, right? And now we are replacing AX with what? Our earlier integral there, right? So AX in there is replaced by integral from YC to D of this one where X is fixed but Y is integrated. Okay? Yes. Yeah, what's the technical name for that? No? Iterated integral. This is the iterated integral, but repeated, but you got the idea. This is the iterated integral, and it computes the double integral, right? But this concept of iterated integral, double integral, not the same thing, but is now connected, right? So this dy and dx, there is a space, wide space in between dy and dx. But in double integral, there's no space. This is 4 letters combined, dx, dy, right? It is not dy and dx. This is 1 letter in there, right? So make sure you use a little bit of space in there when you're doing iterated integral. But this beginning part clearly indicates if it is iterated integral or double integral, right? You never write it like this for double integral. Double integral, you always write it like this. There were R in before. And then f of xy, dx dy. No exception. Just write dx dy. It's a symbol there, all right? Now it is equal to what? Iterated integral. First, sectional area, fix x, and integrate with respect to y first, right? So that inside there represent what? That's right. Jeez. Yeah, that's the sectional area, right? And then you integrate one more time, correct? For x out there. Use a little bit of space. And this is supposed to be the volume of the thing that we started with. That looks reasonable, right? Yeah. Order does matter. So if you have, if you do the other way around, why don't we slice along y first? So you integrate x first. So x coordinate AB goes in there first. So that will be the sectional area for y equals something, like, right? The other way around. So that will be sectional along the different axes. Now then you're doing C and D, dy, right? The other way around. What do you think? These two things should be the same? Right. So I think what I'm sensing is that to some people, must be obvious that should be the same to some people because they're focusing on the way it's calculated. If you think about the way it's calculated, it is not easy to understand why they should be the same. However, if you look at it like intuitively, like a physicist and other people, oh, they represent the volume of the same thing and slice a different way, they must be the same. However, mathematicians don't think like that. Mathematicians think like that if this is our definition of the volume, we have to justify this is a good definition so that however you chop this off, it should remain invariant. Then you can use that, but that doesn't really help that you can just conclude that it's invariant. You have to prove it is invariant, right? So it becomes a serious issue. And especially when you go to four-dimensional space, like relativity, lots of integrals kicking in, you have to understand why they're the same. Because you cannot see it anymore, this business of justifying becomes a serious business. This is called Fubini's theorem. Well, I'll see you later.